Welcome back to another AP Pre-Calc video. I'm Mr. Hibble. Today we are looking at our first section of 3.15, talking about polar graphs now and polar functions. Last section we were looking at simply plotting points, so it's just kind of natural for us now to introduce graphs and how that may work. This is the first part of a series, so the second part we'll start to analyze graphs and intervals with these functions, something that's a little bit more challenging, a little confusing at first, so definitely worth a watch. Make sure you watch the other 3.15 video. So what it says here is for polar function, the inputs are given by theta, and the outputs are given by r. On the AP Pre-Calc exam, questions may use the phrasing below to introduce a polar function. The graph of the polar function r equals f of theta, where f of theta equals 3 minus 3 sine theta is shown in the polar coordinate system. Okay, that's just how they may introduce it. They're saying r is f of theta, and then we have some function. Graphing polar functions, one way you may do this is creating a table. Sometimes we also sketch graphs just on the xy plane first. That can also help you create coordinates based off of what the function is that you're looking at. Let's go ahead and look here. So first thing, let's just talk about where some of these values are coming from. Again, we should know this because they're each just going to be coordinates. Well, for example, we know this first coordinate means that the angle is 0, so we're not rotating at all, but we need to go out to a value of 3. That is this spot. We call that r comma theta, which is 3 comma 0. Okay, remember that's our order for plotting these, or for our coordinates. So the next one then, we have an angle of pi 6. If we need to label those over here, we can. And we now should be at 1.5. So notice when we rotate, we're going to be rotating counterclockwise until I get to pi 6, and I should be at a value of 1.5. It looks like we are. And then that process just continues. At pi fourths, we should be at 0.878. So pi fourths, we'd be at 0.878. Pi thirds, 0.4. And you start to see how this graph is actually formed. We make these dots, we rotate in between them. At pi halves, we're at a value of 0. We're at the origin. And then we start to rotate to the other side. And as we do that, this graph just ends up going around and around until each of these different spots have been found. So there is our graph. That's how graphing these functions works. There's some really crazy graphs that can happen. If you're interested, I urge you to look up just on YouTube or something, polar graphs. And there's some really cool ones. We're going to stick to some of the basics for this class, though. We're going to primarily focus on circles and roses. Well, polar functions can create circles whenever you have something in a form of a cosine or a sine. Okay, so circles are this form, a cosine or a sine. Notice there's nothing that is adding or subtracting with these. There's nothing multiplying with theta. You just have a value, a coefficient in front of the actual function. Well, one interesting thing that happens is where these circles form. Cosine, if we think about cosine as the x and we think about sine as the y, like we typically do for the unit circle, what we're going to notice is these circles start to form around those axes. For example, for cosine theta, we notice that circle is around what we would consider the x-axis. And notice where that value of 4 comes out. 1, 2, 3, 4. It's 4 units from the origin. That gives you the distance from the origin. So if I have 4 sine theta, we know that our graph would go up to 4. It's around the x-axis, and we have our circle. Well, the cycle for this stuff, It really depends on what you're looking at. Whenever you're looking at a circle, the cycle only ever takes 0 to pi. It's never less than that. It's never more than that. Your cycle will always be 0 to pi. That's how long it takes for the polar graph to form a complete circle. If you have a positive case for cosine, like we see here, it would open up to the right. If you, that's not the right, that's the top. If you have a negative case, that would mean it opens up to the left. My first one should be touching the origin or pole there. For sine, if it's positive, we see it was above. And if it's negative, that would just flip it upside down. Let's talk about roses. Roses are slightly more complicated. Circles can be thought of in this same regard, though. The value in front still tells you how far out it is going. But now, whenever we have roses, there's also going to be a value multiplying on the inside. So, roses, the general form we can have is a cosine b theta, or we could have a sine b theta. Those would both give us roses. Well, depending on the value of b, the value next to theta, that determines the amount of petals, and the amount of petals also tells you the cycle that you are looking at. Whenever you have an odd multiplier, what we know is the amount of petals is always the same. But whenever you have an even multiplier, this value of 2 here, it's always going to be doubled. Remember, to double something, you're simply multiplying it by 4. Well, the other weird thing then is the cycle. Whenever you have an odd number of petals, just like when there was 1 petal, right? A rose is just 1 petal. When you have an odd number of petals, the cycle is simply 0 to pi. But whenever we double the petals, the cycle is also going to get doubled. So it goes from 0 to 2 pi. Some other intriguing things to note. Notice where these graphs are formed. One thing that is always true is whenever you have cosine, one of the petals will always be around the x-axis, just like it was for the circles. Notice we have one of our petals here around the x-axis. We have 2 different petals here around the x-axis. That's how we can tell it's a cosine function. Well, sine is either strictly on the y-axis or it's not on any of the axes. Notice for this one, we do have a petal around the y-axis. Realize cosine can be around the y-axis as well. Sine will never be around the x-axis, though. So we know it's on top there on the y-axis. We know the number of petals is odd here, so it's just the value of 5. That means our cycle is just 0 to pi. But now I have an even number on the inside, so I need to double both of these values. The number of petals is 8, and the cycle is 0 to 2 pi. If you were to graph this, what you would end up finding is 8 petals, and you would notice that none of the axes have a petal around them. That means there's 2 petals in each of these different sections. Notice the value of 5, that's where each of these petals should be getting out to, which is all the way at the very end. Notice this is not a perfect sketch nonetheless, but it is 8 petals drawn, showing you the general idea of what happens. If you want to see a clearer image, go ahead and type that into your calculator. So, this top part is exactly what we were just looking at. Is it a line? Is it a circle? Is it a rose? Well, I know this is a rose because of the value on the inside. It's an odd number of petals. The maximum distance from the pole is the value on the outside. Since it's an odd value on the inside, we know our cycle is 0 to pi. When there's no multiplier on the inside, we know it's a circle. This circle is sine. That means it's opening up because it's positive, where the max distance is 9. We know circles are 0 to pi for the cycle. Last one looks like this is a rose. The petals, we double the inside. The max distance is 8. Make sure we double the cycle. One other thing you might look at is creating equations for this stuff, which I don't think is necessarily too challenging. Because all we're doing is we're saying r, or f of theta, is equal to the distance. Well, the distance out is 2 in this case. I notice it's around the x-axis. That must mean this is a cosine function. And since it's just one circle, it's just theta. I look at the next one and okay, how far out does it go? 1, 2, 3, 4. I look at whether it's around the x-axis or not. It's not in this case, so it's sine. There's 4 petals. That must mean the inside value gets doubled, so it'd be 2 theta. And then we could look at this last one. How many down is that? 1, 2, 3, 4, 5. Notice it's negative because it's opening down now. Just 1 petal though, so I'll leave it as a circle. Let's go ahead and look at one of these problems as well. Let's look at number 1. We can still start by analyzing the parts that we have so far. But then maybe we're given a table, right? And that table, all that's really for is to plug in. What is the r value if we know these theta values? Well, we could do that by taking our function that's at the top, plugging in the values. So I have 5 times the first value of pi 6, which is just 5 pi 6. Well, I need cosine at that time. Cosine of 5 pi 6 is negative root 3 over 2. 6 divided by 2, we could simplify that to get negative 3 root 3. Same idea for pi. You could plug in there. R equals 6 cosine of 5 pi then. Okay, but 5 pi, that's not on the unit circle, is it? It's more than a full rotation. So we could go backwards. We could think about unwinding this circle. Well, if I get rid of 2 pi, there's still 3 pi. That's still more than a rotation. I get rid of another 2 pi. That must mean that 5 is the same thing as pi. Okay, well, cosine of pi is negative 1. So we get 6 times negative 1, which is negative 6. These other few problems are just like that. The third one I think is interesting, though, because it's just r equals 7. If you just have r equals, realize what that's going to do. It says you have a radius of 7, meaning out here to a value of 7 or negative 7. And it doesn't matter what the angle is. So I could even go up here to a value of 7. I can even go down here to negative 7. Or I could go somewhere in between and still be 7 units away. And what you start to notice is this also forms a circle where the center is the origin. Your max distance is 7. Your cycle, it is a circle, so it'd be 0 to pi. But this circle had to go around a full time. This one would be 0 to 2 pi. From there, the radius, we know it's always a value of 7. And now we've completed that problem. This was the intro to 3.15. There is another video analyzing graphs more deeply, looking at intervals, identifying certain parts of graphs. Really a good, interesting video there. So make sure you watch that one too. Come back next time.